Hey team, so in this lesson we're going to talk about mass spectra and we're going to calculate relative atomic mass from mass spectra. Now this is a mass spectrometer and this is how the ions that we're going to talk about are detected. We're not actually going to go through how this actually works, but purely because it's not assessed in this topic and it's not really essential. All you need to understand is that a sample is put into the mass spectrometer and it's turned into fragments that have positive charges, and only the positive charges are detected. So before we go any further, what does a mass spectrometer do? It measures the mass of an individual atom, and it can measure the mass of fragments as well, and molecules, but for this type of mass spec we're just talking about individual atoms. Now we know atoms are incredibly tiny and really too small to use in calculation. So here's the actual mass of a carbon atom and the actual mass of a hydrogen atom, and they're really, really small. And when you relate these to each other, that you get 11.92, so effectively carbon is 12 times bigger than hydrogen. We always compare to carbon-12 because it was common, easy to store, and when you used in calculations it produced a really nice number, which is really good. So this is what a mass spec looks like. You can see the spectra here where you've got relative abundance on the left hand side, and down the bottom you've got mass, or M over Z, which is mass over charge. Now the charge is always going to be 1, so therefore the scale is really the mass scale, but it's the mass over charge because all of these fragments have a charge and that charge is 1, so that means that they've lost 1 electron. And so the other key thing to note is that the relative abundance here, sometimes it'll be 100, which will be like 100%, and sometimes it won't be. And so you just need to be careful what the top scale is, and we'll go from there. And I'll show you some different examples as we go through. So this is the mass spectrum for boron, and you can see here that there are 2 peaks. So because there are 2 peaks, that tells us there are actually 2 isotopes of boron. And you can see one of the isotopes has a mass of 10 and one of the isotopes has a mass of 11. And this is how we can put samples of all elements into the mass spec and work out how many isotopes they've got and how abundant they are. And so you can see here that this scale is 100 and it goes right to the top 100. And so that means that we're talking more than 100 atoms effectively if we're wanting to do a calculation. Whereas sometimes the scale might say percent relative abundance. And we'll see an example soon. So if we look here then, I know the scale is painfully hard to see here. If this was an IB exam, it would be much harder and much easier for you to see. But I've told you down here what the abundance is. So boron 10 has an abundance of 23. So you could pretty much say there's 23 atoms in this sample. And boron 11 has an abundance of 100. And so we can actually use their abundances and their masses to work out what their relative atomic mass would be on the periodic table. So let's go through what that calculation would be. So the first thing you do is work out the total mass of those borons. So 23 times 10, the mass is 10, there's 23 of them, and 100 times 11, okay? 11 is the mass and there's 100 abundance, and that comes to 1330. Now we know that we're talking 123 atoms, or we're going to say it's 123 atoms, so we're going to turn those abundance into atoms, okay? So there's 123, so if you take 1330 divided by 123, you get 10.8, and that's the relative atomic mass of boron, and that's what you see on the periodic table. So this is how they've come about. So this one here is zirconium. Okay, and you can see here zirconium has got 5 isotopes, and you can see the relative abundances. Now I know that these are really, you can't see the scale here, so I'm going to have to tell you on the next slide what their abundances are, but we can actually go forward and calculate the relative atomic mass here. Now you'll see this time it says relative abundance as a percentage. That's often, I prefer this as a scale because that means that that's out of 100. So if I show you here are the relative abundances of zirconium. So 90, there's 51.5, so it's the most common, then 11.2, 92 is 17.1, 94 is 17.4, and 96 is 2.8. So 96 is not common at all. So we can go and we can actually calculate this relative atomic mass the same way we did before. So the first step is to calculate the mass of all of those. So you do 90 times how many there are, 91 times how many there are, and so forth. And you end up with this figure here, 9131.8. So that's the mass of all of those isotopes. Now, because it's a percentage, it's going to be out of 100, so we can say 100 atoms. So if we divide that by 100, you get 91.3. And so the relative atomic mass of zirconium is 91.3, which is pretty cool. So now we can look at an example of chlorine. And you can see here this is relative abundance, so it's not percentage, so just be careful to look for that. The approximate abundance of these two isotopes is 75% and 25%, and we looked at this last lesson. What's really useful is you can see on this mass spec, the scale here, this 135 is 3 times taller than this one here, so we say it's in a 3-to-1 ratio. And when we go forward to doing mass spec for topic 11.3, we will use this a lot more when we're talking about the mass spectrometry of molecules. Okay, so we can see there's a 3-to-1 ratio, there are 2 isotopes. This one's present about 75% of the time, and this one's present 25% of the time. And so we could go forward and do a calculation, and so we can, we'll do that. But the other thing I want to talk about with this one here actually is the fact that what's been quite easy about the boron and zirconium examples is that those are elements that do exist as individual elements, whereas though hopefully we know by now that chlorine doesn't actually exist as an individual chlorine. Chlorine actually exists as Cl2. So I'm going to go forward and show you a bit of an example here. So when chlorine is put into the ionization chamber, an electron comes off. Remember I said that we only can, get positive charges. So what happens is the positive charges are then observed on a spectra. And so if we put Cl2 into this mass spectrometer and an electron's fired off, we'd end up with a Cl2 plus molecule, which is fine, that's great. So the thing is though, some of these chlorines would be chlorine 35 and some of them would be chlorine 37, and so that creates a whole lot of different masses that could possibly appear in our spectra. So if you had two 35 chlorines, for instance, you'd see a mass of 70. Or if you saw two chlorine 37s together, you would see a mass of 74. And if you had a chlorine 35 and a chlorine 37, you'd see a mass of 72. And so this fragment here that you would see of this ionized molecule would actually produce 3 different masses right there. And then further from there, it could then split again, and you could produce the 2 fragments for chlorine, and one of them could be 35 and one of them could be 37. So in this spectrum here of chlorine, this is what we would see for just that Cl plus fragment, and you'd see, this and this, But what about the rest of them? What about these molecular Cl2 plus fragments? And so you're actually going to see all of these peaks further up and higher up in the atomic mass Z spectrum, and we just talked about these. So if you saw 35 and 35, you'd see a peak at 70, and if you had 35 and 37, you'd see a peak at 72, and 37 and 37, you'd see a peak at 74. And so this is just explaining it in a bit more detail. So I think that's pretty cool. And so you'd also see peaks up there. You'll notice that the peak at 74 is the least common, and that's because isotope 37 is not as abundant. And you'll see the 35 and 35 is present here. You can see it's 70 and it's more abundant. Cool. So the ratio that are produced with these are 9:6:1, but you don't actually have to memorize this. I know I've just said remember the ratio is 9:6:1, but this is a bit beyond where we're at, but I just thought it was quite interesting to show you. Okay, so and if you look here, you can see this is what the whole spectrum would look like. So these two are for your individual atoms of chlorine 35 and chlorine 37, and these peaks are for your molecules, your Cl2 plus. It's really important when you look at this though that you can't do a calculation of this nature for these diatomic molecules all together. So you can't do the same procedure to work out a relative atomic mass. You can only look at these two for the individual atoms to do that. So you kind of look at this as two different spectra, that this is the individual chlorine atoms and this is the Cl2 molecules. Hopefully that makes sense. So let's go through and look at a couple more examples. So what is the relative mass of rubidium? Okay, so there are two isotopes. This one's 77 abundant, this one's 23. So we would do 77 times 85 plus 23 times 87, and then we would divide that answer by 100. So if we just go forward, that's exactly what we do, and so therefore the relative mass would be 85.45. Let's look at another one. Let's do gallium. There are two isotopes, 69 and 71. Their abundances are a bit hard to read, so I've told you them. So you do 69 times 60 plus 71 times 40. That adds to 100, so we just divide that number by 100. And there's the answer, 69.8. So this one here, now I think in class everyone said don't look at these numbers here because they don't add up right, which is correct. They don't. This value here is missing a 0, and this one here is missing a 0, but you can just use these percentages here. They work great. So this is silicon. So silicon 28 is 92.21% abundant, silicon 29, 4.79, and silicon 30 at 3.09. So if you do 28 times this, 29 times this, 30 times this, and then divide by 100, you'll end up with the answer 28.13. So hopefully this makes sense. So the final example that we're going to look at is bromine 79 and 81. What would the spectra look like and why? The reason why I've asked this is because bromine exists as Br2, and so again it would follow a similar pattern as did the chlorine example. So if we look here, so here are the two isotopes. They're actually about 50-50 abundant, the 79 and 81. But you would also see kind of a separate spectra higher up here, and that would be for the combinations of the different bromines joining together. So 79 and 79, and 79 and 81, and then 81 and 82. Yeah, which is really cool. And what's really nice about this one here is, in this part here, the middle peak's going to be far bigger because this is 50-50. You'd end up with twice the amount of the mixture between them, which is quite nice. So hopefully that makes sense. The last thing that we're going to do just to finish off this lesson is, what if you had to work backwards? So what if you were told to prove work out what the relative abundance of an element is, say boron here. So boron's got two isotopes, B10 and B11, and if you look it up on the periodic table, you'll see that it's got the relative mass of 10.8. So what we could do is actually work backwards from that, and here's the calculation that you would do. So let's do a bit of maths here. Let's just say that X is B10 atoms, and so therefore the remaining atoms are going to be B11. So if we had 100 atoms then, and we're saying that B10 is X, then B11 would be 100 minus X. So the first step to all of these calculations is to work out the total mass. So we're going to take X, which is the mass of B10, times by, which is the number of B10, times by 10 its mass, plus 100 minus X, which is the number of B11, times by 11. And so if you expand that, you end up with this value here, 1100 minus X. The next step is you take this value and you divide it by the number of atoms, and we've said out of 100 atoms. And so then when you plug in the relative mass from the periodic table, which is 10.81, plug it into this expression, you work out that X is 19, which means that B10 is present 19% of the time, and then 100 minus X is B11, which is 81%. Hopefully that all makes sense. Let me know if you've got any questions, and we'll move on to emission and absorption spectra. Thanks.